In exercise 1, we are going to look at the group of elements 1, 3, 9, 11 under multiplication modulo 16. So the operation on this set, our binary operation, is multiplication mod 16. And they're asking us first to make a Cayley table and then to show that G is a group. So let's start by making the Cayley table. So you've seen a Cayley table before. It's really just like a multiplication table, or for our particular type of multiplication, which is multiplication mod 16. So we're going to write down our elements across the top: 1, 3, 9, 11. And across the side, we have 1, 3, 9, 11. And our operation is multiplication mod 16, so I'm just going to write that as a star right here. And so we need to figure out what are the results when we multiply all our numbers together mod 16. And you can stop the video and do this yourself and then see if you come up with the same results that I'm going to come up with. Okay, 1 times 1 mod 16 is 1. 1 times 3 is 3. 1 times 9 is 9. 1 times 11 is 11. Not all that interesting. The same is true. I can fill in my first column. Now let's see. 3 times 3 is 9. Mod 16, that's still 9. 3 times 9 is 27, but we are mod 16, so mod 16, if I take 27 and divide by 16, I get a remainder of 11, so that is 11. And then 3 times 11, that is 33, but if I mod out by 16, I have a remainder of 1. And so in this manner, we can fill in everything else, so try it out, but I'm going to fill this in. And here is my Cayley table. And maybe just one that was interesting, let's write down the operations for 3 times 11. So 3 times 11, that is 33, but mod 16, I get 1, since 33 is 2 times 16 plus 1, and I'm looking at that remainder right here. That's the result of multiplication mod 16. So I have my Cayley table, and now I can use that to show that G is a group. And what we have to show that something is a group, one thing we have to show is that our group is closed under the operation. So if I combine any two of our elements using our operation, multiplication mod 16, I again have to get another group element. So closure. So the closure, we can see that in our table, because all our table entries right here, everything is a group element. We are not seeing anything that's not in G, and that's what closure means. So closure can be seen in the Cayley table. Okay, what else do we have to show? A group has to be associative. So associativity. And if we wanted to show that element by element, or 3 elements at a time, that would take forever. But really, multiplication is associative, we know that, in Z. And since right here our group element really is a subset of Z, we get associativity for free. So this follows, associativity follows because our group G is a subset of the integers, and the integers, Z, that set is associative under multiplication. So we're looking at a small set of a bigger set. The bigger set has this property, so the smaller set just inherits that property. So we get it for free. What is the identity? Okay, let's see. What is the identity? We also can see that in the KD table. So we need to find an element that when we combine it with the other or multiply it by the other elements, we don't change those elements. And if you look at the first row and the first column, you see that we didn't change. We got our elements back when we multiplied by 1, either from the right or from the left. So that is our identity element. So 1 is the identity. And we can see that from the table. 1 times A is equal to A times 1 is equal to A for all A in G, and we saw that in our table. So this is just, again, what it means to be an identity. Now, do we have inverses? Again, let's look at the table. When I look at the table, let's look at 1. Is there something we can multiply by 1 to get 1? Yes, that would be 1. So the inverse of 1 is just 1. Because 1 times 1 is equal to 1. What about 3? What is 3 inverse? So 3 inverse, what do I have to multiply by 3 to get 1? Seems to be 11. It looks like it's 11 because 3 times 11 is the same as 11 times 3 is equal to 1. And in the same way, you can convince yourself that 9 inverse is equal to, let's see, 9, we go to our table and we see that that is 9. Again, 9 times 9 is equal to 1. And finally, what's 11 inverse? Let's go to 11. Up, here we are. That is 11 inverse is 3. And we already wrote that down. You can go back over here. We already wrote that down, the reasoning for that. So every element in G has an inverse. So every element in G has an inverse. So we have a group. We had to check 4 things. We had to show that our group was closed under the operation. We had closure. We had to show associativity. We had to show the existence of an identity. And we had to demonstrate that every element had an inverse. And that together tells us that our group under multiplication mod 16 is a group, that our set under the multiplication mod 16